So we're going to start now the second part of this week's work, which is to do with rotational forces and inertia. Now we're going to mention the idea of momentum, but we're not going to start that until next week. So the good news is that we're already familiar with rotational forces. We learned about them last year. Now I know that torque as a concept strikes fear into your hearts, and I'm glad to tell you that I think that our level 3 understanding of torque, of the idea that we can have an object with a pivot point and we can apply a force somewhere on that object. We could apply it just gently around the middle. And I hope you can see that if I was spinning something just around the middle of its pivot point, I wouldn't get a lot of torque out of it. It wouldn't change its angular movement very much. On the other hand, if I was sitting on the outside, I could change it quite a bit. And we still use our same formula, torque equals force times distance, and we still have the same units, Newton meters. Okay, so torque in level 3 is much more dynamic. It's much less about pivot points and balance and much more about Newton's second law and momentum, which is why I've got that on the bottom there to remind us. Now moving over here, our other new but something we've probably thought about before concept is rotational inertia. And you might think you've never heard of this before, but we could call this, if we wanted to, rotational mass. Now, we're familiar with the concept that a heavy object, an object with lots of mass, doesn't accelerate for the same force as much as something with a small mass. In level 3, when we talk about rotation though, we have to account for the fact that the distribution of mass matters. Now you're already a little bit familiar with this from the idea that, as you would know, things that have a lot of mass around their base are heavy to knock over, are hard to knock over. Things that have a large base, harder to knock over than things that have their mass distributed at the top. And I hope you can understand that that has to do with where the object spins around its centre of mass. We're taking that concept a little bit further and we're saying rotational inertia, which conveniently for us has the symbol capital I, is equal to whatever the mass is times by wherever the mass is in relation to the pivot point squared. Now I've left a little space there because technically it's the sum of all the individual masses. And we've been familiar with this in our centre of mass work, so hopefully this isn't a new concept. Now, I want you to take a look over, before you panic, I want you to take a look over here. Now, let's say this is a solid cylinder, a solid disc, and this one's hollow. Would you expect if we were rolling a piece of pipe and a disc that have the same mass and they have the same radius, but one's hollow and one's full, would we expect them to roll the same way? And I hope very much that your answer is no, even if you can't say why you wouldn't expect them to roll the same way. The answer is that as long as they have the same mass, this one has its mass distributed evenly around the pivot point, around its centre of rotation. So this one here, these ones, this little, I'll get a different colour, this little tiny piece of mass here contributes less to the rotational inertia than a little tiny piece of mass out here, which contributes more because it's further away. But if you can imagine, if the object is hollow, and I'm really sorry about my terrible drawing here, there is no mass here. All the mass is distributed around the edge. So I hope you can see that hollow objects, where the mass is distributed towards the edges, have a different rotational inertia. In fact, a much greater rotational inertia. So we would say that for our hollow one, and I'm going to write it small so I hope you can see it, but for our hollow one, we would say that I equals mr squared, so long as it's sufficiently thin around the edge, so long as it's very disc-like, like a hoop. So a hula hoop would be an example of this. And that's because all the masses are at the same R, at the same radius. They're all located around this R value here. On the other hand, our solid one, all those masses are, some are in the middle, some are around the outside. And if we average them out, we get I equals a half mr squared. We get two different rotational inertias for objects with the same mass. And we'll do a little bit of work on that in class, so don't worry. Now, Newton's second law still applies to everything. As far as we're concerned, Newton's second law is extremely universal. So what does Newton's second law say? It says F equals ma. Now, is there any reason we can think of that couldn't apply to rotating situations? And I hope very much that the answer is no. In fact, we can say, well, the torque is equal to the rotational inertia and the angular acceleration. So just like for an object, any object of a given mass, we apply a force to it and we get a certain acceleration out of it. Okay, so far so good. On the other hand, if we have here, we have a certain object with a certain rotational inertia. When we apply a force to it, we get a certain amount of angular acceleration out of it. And so I hope you can see that if we had two cylinders or two discs or two hoops and we apply a force on the outer edge, it's going to have a certain amount of angular acceleration, just like you see in translational motion. There's just one thing I've forgotten on here, which is up here, the units, and I hope you can see that the units of rotational inertia are kilogram meters squared. Just like the formula, kilogram meters squared. And there's our unit there. I know that this can get a bit confusing because these aren't things we've seen before, but we're going to persevere with them and I'm sure you're going to be fabulous.